So yeah, also when you're looking at these crashes, trying to exploit them, use bang exploitable, see what it says, see if it jumps what you think. If you get one calc, try to exploit one of the other vulnerabilities. There's not just this one. I'm sure some of you have seen other crashes that were a little bit different than this one.
Turn on safe SEH.
You did?
You did.
Yeah.
Says it's
yeah.
This thing's hardened.
Yep.
So then what's in the CDF reader hardened?
I forget what I put in there. Maybe GS protection and variable reordering and stuff like that.
No, it's safe SEH, GS, ASLR, and DEP all turned on.
Hello. Your system should you should have rebooted not into DEP mode here though, but you can, if you want an extra challenge, you can reboot into DEP mode and make your exploit bypass DEP as well.
His point is though that we can't do the trivial like just overriding the exception handler, which is the easiest thing to do because you have SE.
Yeah, you can.
Well, you can, but you can't just point it directly back at your stack.
I have safe SEH turned on, so we can't. That's right, but you can do a pop-pop return, right? So you can't find a pop-pop return in the CDF reader executable, but why don't you look at those other DLLs supporting? Remember what I said, application DLLs do not typically opt in to all this stuff.
Yeah.
And so I didn't look for, the old version of Simple Direct Media Layer, whatever. I just went and downloaded SDL, which is what I used to write the CDF reader, and put it in there, having no idea what sort of exploit mitigations it would turn on. But I sort of suspected it would pretty much be nothing. And see what you see. Because it's importing a ton of application-specific DLLs to do all that 2D graphics rendering. So the game plan is, guys, we're going to take lunch again at 11:15, just here in like 10-15 minutes. And then obviously you can work on this over the lunch break, and I'll give you more time after the lunch. I want everyone to get a calculator for their CDF document. For those of you that get one quickly before others, try to turn DEP on and make your exploit bypass DEP, or try to find another unique crash and exploit that. And then once everyone gets the calculator popped up on at least one CDF crash, we'll move on to exploiting an old Windows vulnerability and using fuzzing to discover it. But I'm going to give you guys some time on this, at least like a couple hours with lunch and all that. All right, so guys, just keep working on the lab, and if you want, I'll start throwing out some hints into my process as I would go through this. So for anyone that wants to follow along with me, I won't do it all at once because I don't want to just give it away. I want you guys to try with it some more. I'll sort of walk through my process for turning the crash 10.cdf into an exploit. So first things first, I'm just going to make a copy of the crash 10.cdf in case I shoot myself in the foot and screw up my file. That way I can revert to the original state. So I'm just copying into exploit.pdf. And what I'm going to do is I want to answer some questions for myself. Where is the min copy called that corrupts the stack? Because I want to break right before that. I've already showed you guys how to do that once, but I'll do it again just for clarity. What are the arguments to min copy? Specifically what? With the address of the buffer and overflowing. Let's see, what is the delta between the overflowed buffer and the exception handler? So I think those are the most pertinent questions for myself right now. So theoretically, what I'm going to try to do is I want to answer these questions, and then I want to change, once I calculate like the delta between the buffer I'm overflowing and the exception handlers, I want to replace those exception handlers with placeholder values like A's and B's, and this just demonstrate that I can gain control of EIP reliably, and that way I'll know which offset in the file represents where I'm overriding the exception handler and gaining control of EIP. Okay, so I showed this last time. Just for finding out the address of where that bad mem copy is called, I run it and let it crash, and then I look at the call stack. And I can see that the mem copy had crashed and the return address was at 4018C. So if I was to look at the code around that address, I should see the call to the mem copy that's corrupting everything. See, that was the return address, and this is the actual mem copy here. So I want to set a breakpoint on this 401187. That way I can look at the state of the program right before the corruption and determine the delta between the buffer I'm overflowing and that exception handler. So let's restart and set a breakpoint on that address so we can look at the mem copy right before it actually goes. Okay, so these are my arguments passed to the mem copy. That means the address of the buffer I'm overflowing is 12FP80. And if I use the Bing X chain, it'll tell me where these exception handlers are located on the stack, so 12FFP0. So the difference between 12FFP0 and the buffer I'm overflowing is offset is OX 230. So at offset 230, well, here's another question we need to answer is the source data for this mem copy, 3843C7, what part of the payload of the file does that represent? Because in this case, it's not going to represent just the beginning of the file, because it's mem copying into part of that header information into a buffer. So let's try to figure out what the source represents in the data. So ESI is still pointing at the source data. And I can see that the source data is equal to this 0-day haiku. So that means in my file, what's getting copied starts at offset 1F. So I'm going to make a note of that. The answer to 4 was OX230. So then another question is, what offset in my file represents what will overwrite the exception handler? Can anyone tell me that with the numbers I have up there right now? So we know after 230 bytes, after we've written 230 bytes into the buffer, we're going to overwrite the exception handler that's stored on the stack from this calculation in number 4. And we know that the data that's causing this overflow begins at offset 1F to the file. So the part of the file that should overwrite the exception handler is located at offset 24F, 230 plus 1F in the file. I'm guessing. So I want to try to demonstrate that now by changing those values in my file with placeholder values and seeing if I get EIP equals those placeholder values when I restart it. The 1F, I saw that the source data being copied into the buffer was a 0-day haiku, and I saw in my file, that begins at offset 1F right here. So you can see the 7A65 and then 7A65 right here. Now, I just sort of came to that conclusion pretty quickly. It might be the case that this data is repeated across the file several times, so I could see this in the file, and maybe that isn't the exact location of the file where it's being copied, but I know from previous experience, this is the only representation of that data in the file. So this must represent at offset 1F of the file where this data is coming from, the source operand for the mem copy. So offset 24F, that should write that exception handler. Let's test that theory out. 24F right here. So I'm going to change this stuff. A. That should be the next pointer for that overridden exception handler. The next one should be the function pointer. So if all this works like I hope it will, when I restart this, I should see EIP equals B. Does anyone have any questions about how I did those calculations? So we know we can't put EIP right at our shellcode though, because we're overriding an exception handler. Okay? So what do we need to point EIP to so we can eventually actually get to our shell code? Pop return. Pop return. So I need to go and find a pop return in a DLL that does not have safe SEH enabled. So I'm going to try to do that here. So political gnarly, do an nmod, see what we got to work with. And look at this, all these application-specific DLLs, like I've said over and over again, do not opt into safe SEH. I didn't turn those off or do any tricks. I just downloaded the simple direct media layer, and that's how they came packaged for me. So I need to find a pop return in one of these guys. And I'll just show you how I would go about trying to find that if I didn't have like a better gadget scanning tool available to me. So I know that just from experience, pop ESI follows return a lot. Like you see pop ESI return a lot. So I'm going to figure out what the bytes are for pop ESI, and search for those bytes in one of these DLLs. It's probably not happy about this because I'm telling it to assemble stuff in unmapped memory. Or just wants to be slow and crappy right now, but hopefully WinDebug will eventually tell us what the opcode is for pop ESI. All right, thank you. All right, 5E is the opcode for pop ESI. Pop ESI, 5E. So I'm going to start searching through those non-safe SEH DLLs and seeing if I can find this byte instruction in one of them, just so I can try to find one pop return in there. All right. So let's start here with SVL image. These are the limits of that. So do a search there at SVL image L. The size of SVL image.dll. Nothing, didn't find anything. So what I'll do instead is I'll just look for a pop ESI, just the 5E byte. That's how I got that. Because the pop ESI often happens around a return, just from experience looking at Windows code. And I can see these. I see a pop ESI and then a return eventually. So maybe I can look at one of these and see what's going on. So why don't I do that? Here we go. That looks promising. So here's a pop return. That was just one way I found one. There's a bazillion, though, in these SVL modules, so you can take your pick. Just do a search for pop ESI, one of them, and then look for it to be followed by a return. Disassemble around what you find and make sure you can get multiple pops followed by a return. It's very common construction in these Windows DLLs, so not very hard to find. But this is the one I'm going to use, and you can write down this address as well if you want to just use the same one as me. what I'll do now is I'll come to HXD and I'm going to replace these placeholder values with pop return. F7. D E4 62. And where should that point EIP at when I execute that little gadget of mine? You remember? Where will EIP end up? Right before. Yeah. So what I'll do is I'll just change these to CCs for now. And what should happen is if this pop return works correctly, I should see a software breakpoint right after the pop return executes. So I can demonstrate control that everything I think is working is actually working. Okay. So I have it executing a software breakpoint. That's good. I've demonstrated control of EIP. My pop return definitely works because it points into a non-safe SEH module. So who remembers what I changed these bytes to so I can get out of this little 4-byte restricted area? Jump 6, right?
Maybe 069090.
06, and it doesn't matter what comes after this, it's jumping over it. So what this should do, it'll execute the pop return, point EIP at this. We only have 4 bytes of space though before that address of our gadget, which we need. So it says, all right, EIP equals this. Let's just jump past this this data I can't touch. I need that address there. And I've got all this to work with for my shellcode. So if I do an EB06, that should technically point EIP at right here in my file. So if I'm sorry guys. Now assuming I have enough space here, past the end of my exception handler before the end of the stack, I can just copy and paste my shellcode here, and it would just jump to my shellcode. But if I recall correctly, my exception handler is located at address 12FFB0. And I know my shellcode is 200 bytes, and so it's not going to fit in that, unfortunately. So what I'm going to do instead is I'm going to put my shellcode in the very beginning of the buffer that I'm overflowing, and then try to jump back to my buffer after I execute that EB06. I don't want to walk through that step yet, though. I want you guys to keep working a little bit on our map here.
Oops, sorry about that. Quick question, though. I'm a little confused on something, right? So when we overwrite the function pointer that's in the SEH handler data structure, right? We're not allowed to point it at, something we control directly. So we point it at a CC byte and we look at the stack and stuff like that. But why is it the case that when we point it immediately to a CC byte and the stack is somewhere else, why is it the case that it's always 2 values onto the stack is the base of the exception handler, like so the first linked list component of it? I guess I'm not clear on why, if we were in the context of the exception handler, I would think that it wouldn't pass control to us passing control to CC before it did any sanity checking. So I'm a little unclear on where the safe SEH sanity checking actually occurs.
Okay, so I showed you guys that offset 254 is effectively what's ending up in EIP, right? Or 253, I guess it is.
Yep, that's specifically the address I'm wondering about.
So you would think that, all right, EIP equals this. I can just point this at a CC byte or or my shellcode or whatever, and since this value gets put into EIP, I'll be good to go. We can't point this directly at our shellcode because the routine that's parsing that exception handler list when an exception happens is saying, this is one of its heuristics, just like a software dev thing. Does this point at the stack? If it does, disregard, do not use. However, we can point it directly just at a CC byte, because if that CC byte is in a non-safe SEH module, it's going to say, okay, that doesn't point at the stack, it points to a code section, and that code section is located in a non-safe SEH module, so it's totally okay. So go ahead and make EIP equal to whatever I put.
Okay, so that's the clarification on the second heuristic, because I had, for instance, pointed it at, forgetting the stuff from yesterday, I had pointed it at a CC within my own thing, but because my own thing was a safe SEH thing, the second heuristic is you may never point into a code region of a module that says safe SEH.
Right, exactly. I mean, technically you can, but it has to point at a function, the beginning of a function that's registered as an exception handler. So that doesn't do you much good.
Right, and actually that was one thing I forgot to comment on yesterday. At some point it would be good if you could show the component, basically where that list of registered safe exception handlers is.
Okay. So yeah, now we got that cleared up. From here, anyone that's still working on this, following me, try to see where you can get from what I just gave you, and then a little bit more, I'll try to work through the process some more. Does anyone have a dev bypass working for the CDF reader as well? No? Okay. Just checking. Does anyone have a dev bypass with a return-oriented payload prepended to it to bypass ASLR as well? Of course, you'd have to go and find all the gadgets in those STL ones, which would be hard to do without someone just giving them to you. Okay, so I'm going to do a few more steps up here for anyone following along with me that wants some more help. So at this point, I've executed my pop return. Jump forward 6 is going to put my EIP right here in the file. Because it's going to hit the pop return. Pop return is going to point EIP at these bytes right here. I change it to a jump forward 6, EP06, which is going to adjust the instruction pointer 1, 2, 3, 4, 5, 6 bytes. So if I redo this, I should get a debugging breakpoint with WinDebug, right as EIP is equal to this. That will allow me to calculate a jump backwards to my shellcode. Now I'm going to put my shellcode in the very beginning of the buffer, which I identified as being right here, Z and 0-day haiku, which I found by analyzing that mid copy call. So let me open up my shellcode here. Make sure you do paste right, not paste insert. Otherwise, it'll shift everything down. Restart. Should hit that CC byte. Yep, right there. That's good. Now I want to calculate the relative jump backwards to my shellcode. So previously, I calculated my shellcode, or my buffer I was overflowing was located at address 12FP80. So if I look there right now, I should see those shellcode bytes. So let's just do that to verify. Yep, and I see the FCE889, which are the telltale signs of my calculator shellcode. Now I want to calculate that jump backwards. So A, jump 1, 2, FD, A0, and enter on a blank line. And I can see the bytes for the jump I need are E9, C3, FD, FF, FF, so I can just hack that into my payload where those CC bytes are currently. Let's see where did I put all that stuff. So I'll set 24F in my file. ABO6, 0000, there's my pop return. There's where my CCs are at, so that's what I need to replace with my jump backwards. So E9, C3, FD, FF, FF. If I do a dot restart, I should get the calculator. Does anyone have any questions about the process I just went through or would like for me to repeat that? I'm going to give you more time so you can make sure you accomplish this on your own as well. But I want to clear up anything with that process I just went through so it's all clear for when you're trying to do it on your own.